Hello. So in the last class we were talking about the thermodynamic behavior of ideal Fermi gas. So we have derived a relationship between various physical quantities in terms of the Fermi-Dirac function f nu of z. Now let us see the limiting forms of these equations. So first let us consider if the density of the gas is very low and or its temperature very high. Okay. So if density of gas is very low and or temperature is very high. In these two limiting cases, so we can write this thing when temperature is very high, so n lambda cube, what is this quantity? N lambda cube divided by g. N is small, so what is this value? This is actually f 3 by 2 of z. Okay, so this is equal to n h cube divided by 2 pi mkt whole raised to 3 divided by 2 dg. So it will be very small compared to 1. So we can write this thing as, so the gas, now this gas can be said, this gas is said to be non-degenerate. Non-degenerate. So the gas is non-degenerate. Okay, and is equivalent to classical ideal gas. Ideal gas. Okay, so therefore we can write f3 divided by 2 of z when this n lambda, when this is very small, this is equivalent to z. Okay, so that means z is very much less than 1. Okay, if nu of z is less than 1, that means z is very much less than 1. So therefore we can write the equation for PV divided by KT. We know PV divided by NKT is equal to, we have derived this thing, F5 by 2 divided by F3 by 2. So this also F5 by 2 also, when Z is very small, F5 by 2 of Z is approximately equal to Z. So this can be written as Z divided by Z. Okay, so this is equal to, so from this we can write PV is equal to NKT. So this is for ideal. So the limiting form is, what is the limit, the condition? When the density of the particle is very low, okay, and the temperature is very high. So when temperature is very high, we know that the quantum behavior tends to the quantum behavior disappears, and we can treat the system as a classical system. So we have this ideal gas become a classical ideal gas for PV is equal to NKT, and U is equal to, what is U? So we have 3 divided by 2 NKT into F5 by 2 divided by F3 divided by 2. Okay, so this is the expression for uh, internal energy, and if we put this limiting value of f of 5 by 2 and f of 3 by 2, then we will get 3 divided by 2 in KT. Okay, which is, we have derived this in the classical ideal gas, same as this. So a Fermi system behaves as a classical system when the temperature is very high or the number density of the particle is very low. Now, and CV, so we have CV is equal to 15 by 4 F5 by 2 divided by F3 by 2 minus 9 by 4 F3 divided by 2 F1 by 2. Okay, so this is CV in K. So this is equal to, so this is Z by Z this also z by z, then it will be 15 by 4 minus 9 by 4, it will be 6 by 4, that is 3 divided by 2. Okay, so cv is equal to 3 divided by 2 nk. So we can from this also we can get cv is equal to 3 divided by 2 nk. Okay, and the Helmholtz free energy a is equal to nkt log z minus 1. Okay, the value of a is nkt log z divided by log z minus f5 by 2 f3 by 2. So we know that when z is very small, so we can write f of z is approximately equal to f3 by 2 of z is approximately equal to z, which is much less than 1. So we can write from this n lambda cube divided by g is the value of f3 by 2 of z, which is very much less than 1. So instead of this thing, you can write z is equal to n lambda cube by g. So we can write from this nkt log of n lambda cube divided by g minus 1. So this is the value of the Helmholtz free energy. Then we can find out the uh, entropy. Entropy, you can find out the Gibbs free energy. Okay, and the entropy is u minus a divided by t, which is equal to, so the entropy of the system is nk 5 by 2 f5 by 2 divided by f3 by 2, nk times 5 by 2 divided by 5 by 2 f5 by 2 divided by f3 divided by 2 minus log z. So from this is equal to 5 by 2 nk minus nk log n lambda cube divided by, okay, or 5 by 2, sorry, or you can write nk into 5 by 2 minus log n lambda cube divided by g. So this is the value of s. So we have derived all the relationship for when n is very much less than 1 and the temperature is very high. Now the next case is if the parameter z is, so z is small, if z is small but not very small, at that time we cannot use, so therefore f of f3 by 2 of z is not equal to z, so we wanted to write z minus z square by 2 raised to 3 divided by 2 minus, so plus z cube divided by 3 raised to 3 divided by 2 minus etc. Okay, so we cannot neglect the z square and all other terms, because even though it is small, it is not very small. Therefore, so we have the number density, that is n by v is equal to n is equal to g divided by lambda cube 3 by 2 of z. Okay, so substituting the value of f 3 by 2 of z from this, we can, and inverting the series, then we'll get the value of z in the form of power series of n lambda cube by g. That is, you can write this thing as some coefficient bn n lambda cube divided by g whole raised to n. So this is the so we can write this thing as power series of z as power series of n lambda lambda cube by b by g. So substituting this value in the expression for p divided by pv divided by kt, which is equal to g by lambda cube gv by lambda cube f5 by 2 of z. So, and using these two equations, we can write the equation of state PV divided by nkt can be written as the power series of n lambda cube divided by g. So that is minus 1 raised to L minus 1 to infinity AL lambda cube divided by g divided by whole raised to L minus 1. So here V is the reciprocal of the particle density, or this is equal to V by N, volume per particle. Okay, so V, small v is the volume per particle. Lambda cube divided by GV whole raised to L minus 1. So this is the equation for PV by NKT. Now here this is the form of virial expansion. Virial expansion. Okay. So we have seen in the case of Bose-Einstein as well. So there the only difference is the alternative term in this expansion is negative here. There all the terms are positive. Okay. Here AL are called virial coefficient. Okay. So this is so we can write PV by NKT as virial expansion. Now here A1 is found to be 1, A2 is equal to minus negative 0.1768, A3 is equal to negative 0.00330, and A4 is equal to minus negative 0.00011, etc. So it goes on diminishing as the consecutive coefficients, virial coefficient goes on decreasing. So we use up to this thing value. Therefore, we can write all the thermodynamic quantities in terms of this virial coefficient, or in terms of the power series of lambda cube divided by GV. So we can use the virial coefficient in all these equations, these virial coefficients. So we can see the specific heat capacity. So specific heat capacity can be written as CV by NK. So CV by NK, what is CV by NK? Is equal to dou by dou T of U by NK. Okay, so this is equal to dou by dou T of 3 by 2 PV by NK. Okay, substituting this value PV by NK from this equation, from the above equation of the virial expansion, you can get CV by NK is equal to summation minus 1 raised to L minus 1. Now there will be coefficient. When we differentiate this thing, we will get a coefficient from this thing. Okay, so there will be one, and PV by NKT is this thing. So PV by NK is T times this summation. Okay, so we will get while differentiating, we will get the coefficient 5 minus 3L divided by 2 into AL lambda cube divided by G small v. Okay, all raised to L minus 1. So we get another summation, another expansion here for CV by NK. So if we substitute the values of these virial coefficient, we get it is equal to 3 by 2 NK 1 minus 0.0884 lambda cube divided by GV plus 0.0066 lambda cube divided by GV whole square minus 0.0004 lambda cube divided by GV whole cube, etc. Okay. Okay, so this is the expression for the specific heat capacity at, uh, at finite temperatures. That means, so we have considered that, so CV is equal to, we have found out that CV is equal to 3 by 2 Nk at T is infinity. At infinite temperature, this is the value. So this is the limiting value of the specific heat. Now, if the temperature is finite, then we'll get the expression in this form. So this is a series, power series in lambda cube by GV. So the specific heat at finite temperature is lower than the limiting value 3 by 2 Nk. Okay. So the specific heat of the gas decreases as the temperature falls. Okay. Decreases monotonically. So like this. So we can draw the graph like this. So specific heat, and here temperature, this temperature, and the specific heat capacity, CV by Nk, CV by Nk. So the limiting value is 3 by 2. So this, if this is 0.5, 1, 1.5. So the specific heat divided by Nk, the quantity Nk is 1.5 at the temperature is infinite. Okay. So at this, at T is very high, that the value is 3 by 2 Nk. And for a finite temperature, the value gradually decreases, and okay. So this is the specific heat capacity at finite temperature. So it gradually decreases with, monotonically decreases with temperature as the temperature falls. Okay. So we have, so far we have discussed n lambda cube is very much small, or n lambda cube tends to 0. So that is called a completely non-degenerate gas. So now we are considering if n lambda cube divided by G is very much greater than 1. Okay. So then the Fermi Dirac functions f5 by 2 of Z, f3 by 2 of Z, f1 by 2 of Z, all these things can be uh, expressed as asymptotic expansion in powers of log Z raised to minus 1. So we can expand these functions in the powers of log Z raised to minus 1. So you can see in this, see appendix E of Path3. Now the gas is said to be degenerate. So the gas is said to be degenerate. Okay. Now let us consider if n lambda cube by G tends to infinity. Okay. So the gas is completely degenerate. So the gas is said to be completely okay. So as T tends to 0, so this happens when T tends to 0, n lambda cube divided by G tends to infinity. Okay. So average number of particles in a single state, that means the mean occupation number Ne will become 1 divided by e raised to e minus mu divided by kt plus 1. So when t tends to 0, this means t tends to 0, this quantity will become infinity or minus infinity. If it is infinity, then this will be 0. If it is minus infinity, this the entire quantity will become 1. So we can have two values, 1 or 0. Okay. 1 for e less than mu 0, and 0 for e greater than mu 0. So accordingly, this will become e raised to minus infinity and e raised to plus infinity. Okay, so where mu 0 is the limiting value of, so mu 0 is called the chemical potential of the system at t equal to 0 Kelvin. Okay, so at t is equal to 0 Kelvin, the level with the E less than 0 is completely filled. All the at t equal to 0 Kelvin, all the levels, all the single particle states with the energy less than mu 0 is completely filled with a particle, single particle per state. Okay, so here if it is 1, so when E less than mu 0, the value of this Ne is average number of particle per state is 1. That means completely filled with one particle per state, and all other levels will be completely empty. That means empty. All other states are empty. Okay, no particles inside. So we can plot the graph like this. So it is, we get a step function, average Ne and the success energy. So this is the graph. So we have, if E less than mu 0, so this is the limiting value mu 0 of the energy, and when this value is, when the energy is less than this thing, the number of particle, average number of particle is 1. Okay, and if it's greater than energy is greater than mu 0, then average number of particles will be 0. Okay, so this is the graph, t equal to 0 Kelvin. So when t equal to 0 Kelvin, so we get a step function for n of E, sorry, Ne, average mean occupation number. Value of the limiting value of the energy mu 0 is called the Fermi energy. Okay, Fermi energy, it is denoted by F. The corresponding momentum is called the Fermi momentum. Okay, like that. Now, we can define the total number of particles. We can define the Fermi energy. What is the Fermi energy? So for that we can take the total number of particles. N is equal to integral Ne average into A of E dE. So we know what is A of E dE. So the total number of particles, if the energy is less than mu 0, that is EF, then the total number of particles will be completely inside this level. Okay, within this level. So that is 0 to EF, N of E, A of E dE. Okay, so this, when energy less than EF, then N of this Ne will be 1. So therefore we can write 0 to EF, A of E dE. Okay, so what is this value? This value A of E dE is equal to, A of E dE is nothing but G times, is the statistical weight due to the spin of the particle, okay, internal structure of the particle. So G times 2 pi V divided by H cube 2m raised to 3 divided by 2 e raised to half dE. So this is the non-relativistic case, non-relativistic. Okay, so here p square by 2m, we have taken E is equal to p square by 2. So accordingly we get this thing, and this is obtained from, so we know the familiar A of E dE is equal to V 4 pi p square dp divided by h cube. Since there is a spin, so this will be we should have a factor g also. So statistical weight g. So this is the expression. So therefore we will get n is equal to the total number of particles will be at t equal to 0. Okay, so this is at t equal to 0 Kelvin. Okay. So n is equal to integral sorry g times 2 pi v divided by h cube 2m raised to 3 divided by 2 integral e raised to half d from 0 to ef. Okay, so this is so we get the final result will be like 4. So here this 2 comes here 4 pi g v divided by 3h cube 2m ef all raised to 3 divided by 2. So this is the total number of particles at t equal to 0 Kelvin. So from this we can write this. We know that the Fermi momentum Pf is equal to root 2m ef. So therefore we can write. So this is one expression. So this is equation number, we can write this as equation number 1, and or we can write n is equal to 4 pi gv divided by 3h cube pf cube. So we can write like this also 4 by 3 pf cube gv divided by h cube. Okay, or we can from this equation from 1 we can write what is the Fermi energy. Fermi energy is equal to, so rearranging this we'll get 3n divided by 4 pi gv. Okay, so we wanted to take the root of this thing, so this thing raised to 2 divided by 3 h square by 2m. Okay, so this is the ef value of the Fermi energy. Or we can write another in another form. We can write 3 n by v is the particle density. N is equal to n divided by v. Therefore we can write 3n divided by 4 pi g 4 pi g whole raised to 2 divided by 3 h square by 2m. So this is the F Fermi energy. Okay, so here we can write this in terms of, so we can put h square instead of a square, we can make it h cross square. So this will become ef can be written as 3 sorry so h square is equal to 4 pi square h cross square. Okay, so we can replace h square by this. So therefore we can write this, if it goes inside then it will be 8 pi cube h cube. So this will be 6 pi square n divided by g h cross square by 2. So these are the two different expression for the Fermi energy. So EF is equal to 6 pi square n divided by g h cross square by 2m, or we can use this expression. So for electron and all, g is equal to spin, the statistical weight factor is Statistical weight is 2, okay, for electron. And write, therefore we can write this EF is proportional to n raised to 2 by 3. Okay, the number density of particles of the system. So the Fermi energy of the system is proportional to n raised to 2 by 3 of the system. Okay. For electron, if we calculate the value for electron, it is G equal to 2. Therefore, if we substitute all the values of these constants, m is the mass of electron, h square is the h is the Planck constant. Then if we substitute all these values, then we will get EF is equal to 3.65 into 10 raised to 3.65 into 10 raised to minus 19 electron volt into n raised to 2 by 3. N raised to n we don't know. For different metals, for metals it is different metals, n is equal to n will have different value. So 3.65 into 10 raised to minus 19 n raised to 2 by 3 electron volt. So this value is in electron volt. Okay. So anyhow, EF is proportional n raised to 2 by 3. Okay. You can say for metals. Metal is a Fermi gas. Okay. So for metals, EF is equal to 3.65 into 10 raised to minus 19 n raised to 2 by 3 eV. Now the ground state energy. Okay. E0. So what is E0? So we can define E0 now. E0 is equal to integral 0 to EF E A of E dE. So substituting here the value of A of E. So we'll get E G times 2 pi V divided by H cube 2m raised to 3 divided by 2 raised to half D. So this is equal to so on integrating this thing we will get or this can be written as is equal to 3 by 5. This quantity is n. Okay, total number of particles in the Fermi level, inside the Fermi level. That means n EF. Okay. So this is the ground state energy E0. So the average energy per particle at in the ground state E0 by n is equal to 3 divided by 5 EF. Okay. So 3/5 of the Fermi energy is the average energy per particle. Okay. So we have in the ground in the at t equal to 0. So all the energy is filled with a single particle in each level. Okay, so this level is called EF and this is the zero energy. So and this energy is completely filled. Now if we take the average, so different value, so each particle will have different energy. So this is the in this axis energy. So energy is continuously increasing and here maximum energy is called the Fermi energy at t equal to 0 Kelvin. Okay, completely filled. All the particles are inside this level. All the particles of the system, whether it is metal, anything. If it is metal, all the particles of the metal at t equal to 0 are below the Fermi energy. The topmost energy is called the Fermi energy. And now the average energy per particle is 3/5 of the 3/5. That means 60% of the energy. So this energy 3/5 of EF is average energy per particle in the ground state. Now this can be therefore the pressure at t equal to 0 Kelvin is P0 is equal to 2 by 3 of energy density E0 by V. So we know for Fermi gas P pressure is equal to 2/3 of the energy density E0 by V. Okay. So from this we can write 2 divided by 3 NEF divided by V. Okay, N by V is the number density. So therefore we can write 2/3 of N times EF. So pressure at t equal to 0 Kelvin is of a Fermi gas is P0 is equal to 2/3 of N times EF. Okay. So anyway, so we know that EF is proportional to EF is proportional to N raised to 2 by 3. So therefore P0 is proportional to N into N raised to 2 by 3. So this is pressure is P0 is proportional to pressure of the gas is proportional to N raised to 5 by 3. Okay. So this is the pressure of a gas in at t is equal to 0 Kelvin. So the 0-point motion is a quantum effect rising due to the Pauli principle. The particle constituting the system cannot settle down to a single state and are therefore spread over requisite number of lowest available energy state. Therefore, the Fermi system, even at t equal to 0, is quite live. Okay, 0 Kelvin പോലും എന്താണ് ഒരേ സിംഗിൾ സ്റ്റേറ്റിൽ ഒരുപാട് നമ്പർ ഓഫ് പാർട്ടിക്കിളിന് ഒരിക്കലും പറ്റില്ല. മാക്സിമം നമ്പർ ഓഫ് പാർട്ടിക്കിൾ ഇൻ എ സ്റ്റേറ്റ് അറ്റ് എനി ടെമ്പറേച്ചർ ഈസ് 1. Therefore, the Fermi system even at t equal to 0 Kelvin is quite live എന്ന് വേണമെങ്കിൽ പറയാം. Okay, so this was the case when n lambda cube tends to infinity. So we have discussed n lambda cube, the limiting cases when n lambda cube by g is very much less than 1 and n lambda cube by g tends to infinity. So now we wanted to discuss the n lambda cube by g is finite. So that we will do in the next class. Okay, thank you.